This video discusses the process of map abstraction. The world is a really big place and it is filled with a lot of stuff. This stuff includes rivers, mountain ranges, forests, cities, as well as people, votes, cars, and ships. So how do we get all of this stuff into a computer? And in particular, how do we map it within the context of GIS? The process by which we take real-world phenomena and transform them so they can be represented as a map is called map abstraction. Now, there are a range of decisions and choices that we must make when carrying out or performing map abstraction. One of the first choices we must make whenever we create a map or construct a database for geographic information systems is what to include within our map and how do we include it. Now, the inclusion and exclusion of various features, for example, rivers, cities, or people, is often a function of scale. Now, scale generally refers to the factor by which we have to reduce the surface of the Earth in order to represent it on a map, and this is sometimes expressed as text on a map. For instance, 1 inch equals 1 mile is an expression of scale, or it can be represented mathematically as a ratio, where you have one map unit over a ground unit, or a measure of distance in the real world. So you might see something like 1 over 24,000, which refers to 1 unit on the map, is equivalent to 24,000 units on the surface of the Earth. In conjunction with the determination or selection of a particular scale at which we want to include or exclude any geographic feature is what is called a map projection. Now, as you know, we live in a three-dimensional world. The Earth is round and spherical, floating through space, despite what the flat earthers may think. And put simply, a map projection is the mathematical formula that we use to transform the three-dimensional Earth into 2 dimensions so the Earth can be represented, for example, on your computer screen or in a book or as a hard copy map. So scale and map projection are very important considerations and processes to think about when working with geographic information systems and maps in general. One thing with respect to scale that is worth emphasizing is the relationship between the detail you might see on a map and the area or extent or coverage of a map. So for instance, we often refer to maps as either large scale or small scale. And some people think large scale refers to the amount of detail that you might see, and small scale might actually refer to the size of the features, when in fact, when we use the term large scale and small scale formally, for instance, within the context of GIS, what we are referring to is the expression of scale as a representative fraction. Recall that the representative fraction is simply the map unit over a real world unit. So you might have 1 centimeter on the map is equivalent to 1,000 centimeters in the real world. And if you compare that number, 1 over 1,000, to, for instance, 1 centimeter on the map over 10 million centimeters, the second number is much smaller than the first. So therefore, 1 over 10 million would be considered a small scale map, which has a large extent, but you can see relatively little detail. Conversely, 1 over 1,000 compared to 1 over 10 million is larger, so that would be the larger scale map, in which you actually have a smaller area covered, but you get to see more detail. Like scale, map projections are a very important aspect to geographic information systems and mapping in general. Map projections involve moving from the three-dimensional world to 2 dimensions. So again, we live on a three-dimensional Earth, we travel through it, we touch it, we feel it, and we sense it in 3 dimensions. However, the medium of representation is generally 2 dimensions. So for example, a computer monitor or a physical map is a 2-dimensional surface, and when we want to represent the world, we have to figure out how are we going to move from the 3-dimensional world to the two-dimensional surface of representation. One way to think about map projections is to imagine the Earth, or a globe, let's say, and you stick a light bulb in the center of the globe, and you turn it on, and around that globe you put a lampshade. When you turn on the light will pass through the globe, and on that globe you have the continents and you have the lines of latitude and longitude, and those features will cast shadows onto the lampshade, or those shadows will be projected. This is more or less the process that we are using to transform or to represent the three-dimensional features of the Earth onto two dimensions. Now you might say, well, is a lampshade really two dimensions? It is. For example, if you were to cut it with scissors down one side, you could lay the lampshade flat. One thing to keep in mind when we work with map projections, or when we move from the three-dimensional globe to two dimensions, is that distortions will be inevitable. And these distortions occur in terms of distance, angular measures, as well as areas. Again, a subsequent screencast will cover projections in a little bit more detail, but it is important to put them on your radar. Once we determine what we want to map or include within our GIS, we have to make a determination of how we want to do so. In that sense, we have to take a step back and recognize that the Earth is made up of various features. Now, features in technical terms simply refer to the parts, characteristics, or qualities of the Earth and its surface. So that could include roads, streams, mountain ranges, as well as temperature and elevation. Features are represented in one of two ways in GIS. First, there are discrete features, which are clearly defined with an edge or a boundary. Discrete features are also easy to locate, measure, and count, and they are readily seen. So, for example, we can consider buildings or represent buildings, roads, fire hydrants, parks, and property boundaries, as well as country boundaries, as discrete features. On the other hand, continuous features are those things that lack a clearly defined edge or boundary, and those things that change gradually over a relatively large area. In this sense, continuous features are not typically seen visually, but they are measured using any number of instruments. Examples of continuous features include elevation, temperature, as well as rainfall. Once we determine whether a feature is discrete or continuous, we need to figure out how we want to represent the real world within our GIS or our map. And like discrete or continuous features, there are generally two ways to do so. We can use a raster model of representation or a vector model of representation. If you think back to your mental maps, you more than likely represented Los Angeles as a series of discrete features. So locations of interest, such as campus or LAX, might have been defined by a single point to which we can assign a specific latitude or longitude. Similarly, a line is simply defined by two or more vertices. So if we wanted to start a line in one location and end it at another and have that represent a freeway, all we need to know are those two coordinate pairs. Similarly, we can circumscribe an area as a polygon if we have three or more vertices or sets of coordinates, with the last coordinate being the same as the first to kind of close the circle, so to speak. The vector data model is typically used to represent discrete features on the surface of the Earth within GIS. To give you a stylized version of the process by which we turn the real world into a vector data model, consider this image here of a landscape where we have trees, a lake, roads, and some buildings. So, for example, if we wanted to digitize these features for use in GIS, we could digitize the trees as individual points, the roads as lines or vectors, which again are defined by endpoints and start points. And finally, buildings, lakes, and other features can be defined as areas. Not only does a GIS permit us to represent these features in vector format as a point, line, or polygon, but we can introduce any number of styles, such as change the colors or symbology, and that is what is behind making a map. Complementing the vector data set are raster data sets, which are used to represent continuous features such as temperature and elevation. Raster data sets are constructed out of rectangular or square grids that are draped over the area of interest. Now, each grid or cell within a raster data set is based on geographic coordinates, so that we know, for example, the specific latitude and longitude of each and every corner within a particular data set. Each cell also contains a value which represents the feature of interest, whether that is elevation, temperature, or even rainfall. And the value ranges are based on the resolution of the raster data set. The resolution referring to the smallest distance between two adjacent features that can be discerned within an image. For example, one square might be 5 meters by 5 meters. Therefore, the resolution for that data set would be 5 meters, meaning the smallest thing that you can discern or see within the raster data set would be 5 meters. Just to visually compare the stylized versions of the raster and vector data models, if we consider the real-world image, and on the top we represent it as a vector data model, and on the bottom as a raster model, you can see the differences where the vector data tends to represent reality as we see it. The raster data model seems more pixelated, but it is more complete in that every cell contains a value. To review, the map abstraction process refers to the steps and decisions that we must make in order to get the real world into a map, whether that is a paper map or a GIS. And this requires a range of decisions about what we want to include and how we want to represent these features. Among the most important considerations are those concerning the map scale, where we make trade-offs in terms of the amount of detail we see and the area covered, as well as projection in terms of which distortions can we live with and which ones can we not live with. Next, we need to consider how we want to represent the features of the Earth within the digital environment based upon how they are measured, either as a discrete feature or as a continuous one. So again, understanding these high-level decisions behind map abstraction will facilitate our learning of geographic information systems.